We organize his memory every around his close to his birthday and birthday. And he was, I mean, we are all, he was alive, whoever was there. We are all very, very connected, both from academic point of view and as well as to be helpful administratively. He was committed to, he was one of the rare persons who was committed to both administration as well as and very versatile. Whenever there is a problem to any student has a problem, whatever subject, you go to him, he will solve. He will give at least a very good hint. I have myself, our subjects are not at all same, but I have myself benefited. And unfortunately, he passed away just at the age of 66, soon after his retirement. We were all very emotional, very sad, very this. At that time, I was the head of the department in Kolkata, and I was requested whether something should be done. And this is what I do. And today's speaker is Professor India. Many of you must have heard him. He's a very renowned mathematician. We two are almost same age group. Our things ran parallel. He was in Delhi, I was in Calcutta, research scholar together. PhD also around the same time. Postdoc also around the same time. In fact, jobs were also offered at the same time, but he stayed a bit longer in Bombay University, so he joined. And with this guy, and he is also a great admirer of Bagchi, very good friend, and he had certain serious difficulties in traveling. In spite of it, for the love and to pay the homage to Professor Sumesh Bagchi, he has taken trouble. It is really trouble I can realize how he has come and come here. For that I am very, very grateful. Thank you very much. And I take this since I am the chairman of ISI Alumni Association. I take this opportunity to request all of you to become a member of ISI. Okay? It will cost
only the alumni.
alumni.
Only the alumni. Only saying you are requesting only the
You are
alumni. not
requesting
the others.
everybody, but I don't think those who are not alumni can become.
Wait, I know ISI very well. There is not a single person here who is not an or going to be an alumni. Like, okay, there is one who is going to submit PhD. I don't know whether you did in math here? No. But she will become. So raise your hand, any of you who is not an alumni. See, I know I said so. I request that everyone. You will let?
You are assuming that everyone will either yes, sir.
Stand or not, well,
I am saying that if you are not an alumni, there are postdocs who are not never at ISI. No, so you have to get. So requirement is eligibility criterion is that you have to get a degree from us.
Yes, they have got their
What do you think that there's nobody?
Actually, you can amend the rule to allow the postdocs also. Yes.
Okay, so your suggestion is taken, we will discuss. But this is the requirement, and all that you have to do is that you go to ISI web page, then there is a section called ISI Alumni, Alumni Association, you press that, then you will come to ISI Alumni Association web page, then there is how to become a member. You do that, a form will come, and the membership fee is 1,000 rupees, till you go to US and start earning in dollars. Then it will come. Okay, so yes. घटिया ठीक है तो बोलना जाए छोटा
I am very happy to be here. Somesh was a major attraction in the old days of coming to ISI. Very good friend for many years. I think he's okay.
I don't know. ওটা তো ভালো ক্যাচ করা যাবে কি অনলাইন
ক্যাচ করছে
We served on many committees for many years, and he was a very conscientious member of every committee. But one small incident I would like to recall. In 2006, the International Congress of Mathematicians was in Madrid. And on one Sunday, we went for a small excursion. I've forgotten who the other people were in that party. But one mathematician, a little older, and I noticed Somesh was sort of providing an umbrella to him, always following him that he shouldn't fall, he shouldn't stumble. And that mathematician was not all that old. And I then came home and checked their ages. He was just 1 year older than Somesh. So that typically captures Somesh's personality, always very courteous, kind, and caring. So I'm very happy to be paying homage to him. So I want to start with a small story. When Satimohan and I were young, one of the famous directors of Hindi film music was a person called O.P. Nair. Maybe you have heard his tunes. Almost the first song I remember as a child, Deke Pehla Pehla Pyar, was O.P. Nair. He usually based his music on folk tunes of Punjab. So once the great Indian Hindustani vocalist, Ustad Amir Khan, the greatest musician of that time, complimented him, भाई कमाल कर दिया, एक ही राग पे एक ही फिल्म में 4 गाने दिए. O.P. Nair looked puzzled, पर कौन सा राग है वो? So it's something like that. I have played throughout my life with matrices. And from time to time, I find it is also non-commutative analysis, it is quantum analysis, it is differential geometry, it's optimal transport. But I know it only as matrix analysis. So I hope to convince you that looking at things from that simple perspective is often very fruitful.
ওটাকে প্র্যাকটিস করলেই ক্লিয়ার
So just to recall something for you, I'm going to talk of n cross n matrices. So this we think of as some kind of generalized complex numbers. Within that, Hermitian matrices. So this you think of as real numbers. Within that, positive matrices. And this I think of as positive numbers. And I have an inner product, which is this A star B. And this gives the norm. I'm just recalling 3 or 4 elementary facts. So this is the true norm. Positive definite matrices I will denote like this. And without saying so, I'll assume they are non-singular most of the time. So everybody remembers from the first course that A is positive definite if and only if I can write it as M star is any matrix. Then A is also N star provided N is M times unit. Every positive definite matrix has a unique positive definite square root. The most interesting thing is that if A and B are positive, that does not mean that AB is positive. So product of two Hermitian matrices is Hermitian if and only if they commute, which is the trivial case. However, if A is positive, then X star AX is positive for all X. And in particular, if A is positive, then A half, B A half is positive. So this fact will occur repeatedly in my talk. I just wanted. Okay, so in the rest of the talk, I'm going to tell you the story of my involvement in one or two problems.
There is a wire.
He's saying be careful.
Be careful, yes. Thank you, yeah. So a few years ago, I came across this expression, A and B positive, trace of A plus B minus trace A to the power 1/2, B A to the power 1/2, and the square root of that, and the square root of this whole thing is a metric. Can you see the board clearly?
It's faint.
The pen is a little thin.
Can you use the blue one, but here?
Sure. Because the black is more visible from a distance. So trace of A plus B minus trace of, so as I just said, this matrix is positive definite, it has a positive definite square root. This is a metric. This intrigued me a little bit. So this is called the Booz-Wasserstein. Booz is from quantum information theory, Wasserstein from optimal transport. So it piqued my interest why this should be a metric, what is it good for. And from the perspective of what I call matrix analysis. So let's look at these two things. Sorry, I made a mistake with the 2 here. So if you look at A 1/2, B A 1/2, to the power 1/2. Yeah? So this is some kind of geometric mean. You see, one of the themes I will pursue is how to write a good version of square root of AB when A and B are positive definite matrices. Because AB is not positive definite, so square root doesn't make sense. So what exactly to do? So this is one candidate for a geometric mean. If A and B were to commute, it just becomes square root of A. And so this inequality compares the arithmetic mean with the geometric mean with a trace here. This is not correct what I have written. But a few years ago, with a colleague called Kitame, who is a Palestinian. Uh, I took this in. All the eigenvalues of the geometric mean are smaller than the corresponding eigenvalues of the arithmetic. So this is a good version of the arithmetic geometric mean inequality. So that at least tells you this is something positive. But that doesn't prove the triangle inequality, of course, which is much harder.
You don't mean multiplication, no? You mean the eigenvalue.
The jth eigenvalue.
Yeah, you mean the jth, the whole expression is jth eigenvalue. Not that they multiply by that.
No, this is the jth eigenvalue of this matrix
Okay.
is smaller than the jth eigenvalue of this. See, there's a general philosophy here
But how do you order eigenvalues?
in decreasing order. Okay, so since this question has been asked, so if the A and B are two positive definite matrices, the strongest thing I can try and prove is this, which means y minus x is positive definite. If this doesn't turn out to be true, I try the next level thing. Maybe all the eigenvalues of x are smaller than the eigenvalues of y. If A and B are Hermitian, always assume the eigenvalues are arranged in decreasing order. If this is not true, then maybe trace, maybe something else, maybe norm. So that's the hierarchy of inequalities. So this is the best version of the arithmetic geometric mean inequality. So that's why I was drawn to this expression. But if you investigate a little further,
There is a cloth here under the plastic.
so if A and B were diagonal matrices or probability vectors, so say P is P1, Pn, Q is Q1, Q2, Qn. So if A and B were commuting, this just becomes the distance between the vectors square root of P and square root of P. And in statistics, this is called the but. So just let me expand. That is. This is called the Bhattacharya distance or the Hellinger distance in statistics. It has been used there. If I was to directly imitate this, I would get which is trace of A plus B minus So notice a subtle difference here. Here is something which could have worked as geometric mean. And here is something different. This is much easier as there's nothing more to say after this. Obviously, it's a metric. But that's more interesting. So again, this is very typical for matrix analysis. Different versions of the same scalar quantity. You will see more versions of the geometric mean in a while. But this is easy. So let me mention, for example, I could look at this. This is not positive definite. I could look at what I've written there. It is positive definite, but it's not symmetric in area. So it leads to some problem. So what is it that I could track? One possibility is exponential log A plus log B over 2. If A and B are positive, they have logs which are Hermitian matrices. So this is Hermitian. You take exponential, you get back a positive definite. So this is now symmetric, but it has its own problems. The version which is most fruitful but mysterious, I'll talk about this a little later. Looks curious, but it's very important. I'll have time to mention this. Strangely, this is symmetric in A and B, though it doesn't look like that. And it has very good properties, which I'll mention later. But let me come back to that. So ISI is the right place to talk of these things because lots of contributions in the old days from C.R. Rao, Bhattacharya and others. Yeah. So given positive A, let me look at this FA. We all M such that A is equal to M star. As I mentioned, this is also the collection square root of A times U, where U is unit. So given AB, now I want to look at distance between F of A, F of B. So this is minimum. Where U is unit. Now this happens to be a famous problem in psychometry of all places, statistics. And I first learned about this from one of C.R. Rao's papers, called the Procrustes problem. This is precisely the problem which I am grappling with, minimum U, except A and B are arbitrary now. The motivation is you have two data sets A and B. If A is equal to BU, then they are just rotations of each other. And you may be wasting a lot of time, computation, money, and so on in trying to compute both. But you can avoid that if you solve this problem. Procrustes, by the way, in Greek mythology was an innkeeper who had a fixed size bed. And whenever a guest came who didn't fit into the bed, he would cut off his legs to fit in this way or that. So, good story, but that's why it's called Procrustes problem. And the solution to this is well known in statistics books. And it is the minimum is attained, and this is an easy computation. Minimum when U is the unitary factor in the polar decomposition of B star A. So B star A, polar decomposition means this is U times absolute value of B star A, which by definition means U A star B, B star A square root. It's a good thing to teach in your second linear algebra course. So you will see this looks something like this. So the solution of this is related to this problem. So using that, you can prove fairly easily, on one page, that this minimum distance is precisely that DAD. So that metric is actually solution of this minimization problem between two fibers, FA and FB. And therefore it's a metric in particular. So that's one good way of looking at it. In quantum information, this is being called fidelity, this expression. Usually in quantum information context, A and B are positive matrices with trace 1. That's the analog of probability vectors. So this is called fidelity. And I'll explain why. This is interesting. So let me write one more expression. So trace is invariant under similarity. Therefore, this is also equal to trace So apply the matrix on the left and its inverse on the right. So this is similarity which keeps invariant the trace. So this is also trace AB to the power 1. Yet one more version of a candidate for geometric mean, though this is not symmetric. So I will use this. So if A and B were pure states, as they are called, that is A is equal to UE star and B is equal to VB star, where U and B are unit vectors, then you can see, which I've just shown you, is also trace square root of AB. So this just becomes the inner product between U and B. And if A and B are density matrices, A plus B over 2, trace of that is just 1. So in this case, this F AB is just 1 minus So this is the correlation between U and V. You have subtracted that from 1. So this is obviously a metric on the relevant trait space. And this is a matrix generalization. So I said this is an interesting quantity. So people try to find its characterizations. Prove it's convex, concave, and has some other properties. It's useful to have what are called variational principles. So here is one of which I will show you a simple proof. F of AB. So one theme running through matrix analysis is using block matrices. Somehow many problems become easy if you go to 2 by 2 block matrices and come down again, as you will see here. Yes?
F of AB is wrong.
Probably this one.
Yeah.
So if you remember, my expression was trace of A plus B over 2. Oh, I am just playing with the factor 2 here and there. This I have called fidelity. And when A and B are pure states, which means A is equal to U star, B is equal to V star, then this factor is just inner product UV. And this one is just 1 because A and B both have trace 1. So this becomes
NDA.
Oh, I'm sorry. Sorry. Yes, yes, that's the X. Clock here. You're aware of the time. Let me show you.
Yeah, enough.
No, I'm not running out of time. I just want to pace my lecture accordingly. Yeah. So one of the expressions for fidelity is the following. It's maximum of trace M. So A and B are given positive matrices. Look at all M which make this positive. Then look at the trace of all those matrices and maximum. That's an expression for the fidelity. Okay, let me indicate a proof at least in one way. So assume this is true. So as I said, a major theme in matrix analysis is going to block matrices and doing various characterizations there. So you imagine something from 2 by 2 matrices and hope it will be true for 2n cross 2n matrices. Often it's false, then you have to modify. So when is such a matrix positive? So one of the known good characterizations is that n is equal to square root of a times k times square root of b. That k is a contraction. See, if these were numbers, a 2 by 2 matrix is positive definite if and only if the diagonal entries are positive and the determinant is positive. Which means m square is less than ab, which means m is less than square root of ab. In matrices, that's not quite correct. So you have a modification that m is equal to a to the power 1 half kb, where this is a contraction. So from this, you can see that trace of n, which is trace of a to the power 1 half k. Trace is commutative, so this is trace b half a half k. A little bit of functional analysis. This is always less than or equal to the trace norm, which is the sum of singular values of this. So that's where an inequality comes in. Then you can knock off this trace. And that is just so at least one way, if this matrix is positive definite, then trace of m is smaller than this. I will leave it as a small exercise. You can see that the maximum is attained when we put m is equal to ab 1 half. Use this in the next thing, which is connection with optimal transport. So what is the optimal transport problem? Let's say we have this furniture lying in this room and you want to shift it to some other arrangement and you want to do it at minimal cost. So abstract version of this. So mu and nu, two probability measures. Let's say Rn. The problem is so Cxy, a given function, the jargon called the cost function, that's the cost of moving material from place X to place Y. So here is a minimization problem. The gamma I measure on Rn cross Rn with marginals mu n. So that is interpreted as the cost of shifting. So think of the distribution of mass here as one probability measure. You want to shift it to something else by lifting it. So that's the idea. And it is known that under some conditions, of course, on measures and on the cost function, this problem has a unique minimizer. And it gives a metric on measures. That's important. So D is for the special function. So this is the cost of moving material. Under some conditions, this has a unique solution, which is called the Wasserstein distance, W for Wasserstein, or Kantorowicz-Rubinstein distance between the measures mu and n. I'll discuss a special case of this, the Gaussian case, which leads to matrices, and that's very interesting. So I'm giving you the connection between this and the optimal transport problem. So suppose x and y are two random vectors. Normal distribution with mean 0 and covariance matrices n. And the problem is, so if those like me who don't know too much about the statistics language, this just means A is the matrix whose ith entry is the expectation of xi bar x. So I want to solve this minimization problem. So this is a cost function. I want to minimize this, subject to that the variance matrix, covariance matrix of X is A and the covariance matrix of Y is B. So that's the Gaussian case of that problem. So let me write the covariance matrix. The 2n vector xy. So this is so the diagonal entries are A, B, and here is what I put as M, where M is matrix. So our problem was to minimize this expectation. Which is expectation of trace x minus y star x minus y, which is trace E x minus y star x minus y. So if you expand this, you get trace of A plus B minus 2 times real trace M. So minimizing this is the same as the problem of maximizing trace M, subject to A, B, and M star being positive, like this calculation. So which is the fidelity? The answer to this is, as we saw, is the fidelity between A and B. So this metric which I wrote down is actually the optimal transport metric. So this answer to this so that's one place where it occurs and it's very important, as you can see. It's not just any expression cooked up. It's the solution to this important problem. Any question or comment?
Yes, minimization is for all joint distributions. Having
Yeah, so the constraint is that A and B are the covariance matrices of X and Y, and you have to minimize this function. Now let me go back to the geometric mean. So how do you write square root of AB in a good way? What's a good way, first of all? So a mean should have certain properties. And there are demands from different professions, different disciplines. So for example, those studying CT scans, so they inject some dye into your brain and they chase it, you get what they call diffusivity matrix. Now, one scan can't give you the entire picture, so you have to average over various scans. So average normally we would think of as A plus B over 2. Determinant of that matrix gives them the volume of water in the brain tissue. So vaguely we accept these things, determinant is volume of something, they are using it. So here is an example. So I averaged my two matrices and I got a determinant which is bigger than both the determinants of A and B. So you get misleading information. This is called swelling phenomenon in MRI literature. You see or interpret a swelling where it isn't there. So they ask us, give us a mean which averages the determinants. So for example, that's one of the requirements. There could be others, I'll talk about some of those. So arithmetic mean fails here. So long ago, mathematical physicists introduced this expression called the Post-Voronovich mean, which is given by if A and B commute, this is just square root of it. That's one of the requirements. Electrical engineers at the same time, or a little before, did it another way. Look at this matrix equation, which is called the Bagchi equation. A and B are positive definite. Then they proved that this has a unique positive definite solution. So you see A and B were numbers, this is just x square is equal to A. So we are trying to write, of course they could not say it that way, we are trying to write square root of AB in some good imaginative way which will work. And miraculously it's the same thing here. Then functional analysts had another way of looking at it. This turns out to be maximum of all x, where x is Hermitian and AXXT is false. To create a 2 by 2 matrix having A and B on the diagonal, put Hermitian x here, then you have to prove among all such x there is a maximum, and that again turns out to be this. And this has been very useful in various things in mathematical physics and in operator theory. And for a long time there was this problem how to do it for more than 2 matrices. So if you look at these, how do you do it? For 2 it's already very complicated. What do I do with 3?
What do you mean by that? I didn't know.
On Hermitian matrices, there is a natural order. X is less than or equal to y means y minus x is positive definite.
In that already there is a unique maximum.
There is a unique maximum which turns out to be this. And this is very helpful in solving issues about concavity, convexity, entropy, and so on. I will not go into that. So, for many years, people were wondering how to define a good geometric mean for 3 or more matrices. And then what helped was something from differential geometry, Riemannian geometry. That's what I will try to briefly explain. But before that, maybe I should tell you something else a little bit. So what are the problems typically caused by non-commutativity? Let us see. So what should a mean do? So I have positive numbers A and B. I want something called the mean. So everybody would agree that it should be, so let's say A is smaller than B. So numbers you can assume one is smaller than the other. Then the mean should be in between A and B. So here I have positive matrices. At the very first step, this is not always true. 2 matrices, positive matrices are not always compared. So I can't write anything corresponding to this, except I can demand maybe if A is less than B, then the mean should be in between. I may demand symmetry. So the same thing here, no problem. Then I may demand if I increase one of the components, if A is less than or equal to A prime, then again these are numbers here on the left hand side. So the mean should be monotone in each of the variables. It should be homogeneous. If I multiply both numbers by a positive number alpha, then the mean should also be multiplied the same thing. What about this side? So here I can demand if we'll come back to this in a minute. And here the corresponding thing is mean of x star ax, x star bx. I want a matrix multiplication. So instead of just multiplying by a positive number, I am doing an operation which is like multiplication by a product. This has interpretations in electrical engineering. This is called the transformer equation for some reasons. And this is very problematic.
Did you also want like mean of the same numbers equals that number itself?
Yeah. That will follow from these. Yeah. Yeah, of course, put all the reasonable properties, continuity, etc., etc. I'm emphasizing those which are source of problems and unique to matrix analysis. So there's a whole theory, deepest theory in matrix analysis, and maybe a good part of analysis called matrix monotone function. Again, I don't have time to get into this here. But suppose A is bigger than B, then is, the first time you see it, you are shocked. So I hope you haven't seen it. Is this true? Everybody would think yes. So here is an example. Take A to be 2, 1, 1, 1. B to be 1, 1, 1. Then A minus B is 1, 0, 0, 0, which is clearly positive semi-definite. So A is bigger than B. A square is 5, 3, 3, 2, and B square is equal to 2, 2, 2, 2. So A square minus B square is 3, 1, 1, 0. The determinant of this is negative. So A square is not bigger than B square. So such a simple function as square doesn't preserve order. So what are all functions that preserve the matrix order? There's a very deep theory there due to Lerner of matrix monotone functions, and very interesting answers. It's linked with complex analysis, harmonic analysis, and so on. But let me say how this property forces the mean to be what I thought. So that thing which looked funny, Voronov formula. Can we have this on? This either a fan or AC if possible. If standing and talking, it's a little warm, but it's fine. So let me denote by congruence by x, this operation x star ax. So I have two positive matrices A and B, and I'm trying to get hold of a mean of them, or some function. So do gamma A minus 1 half. So this pair becomes identity A minus 1 half be A minus 1 half. Now I have two matrices, one of them is identity. So I'll be stupid to do anything else than take the square root of this. So the mean of these two has to be A minus half, be A minus 1 half, 1 half. Now undo what I have done here. And you get so if I have this condition, which is very natural, and I have the requirement that the mean of commuting matrices A and B should be square root of AB, then there is no choice but to have this expression as B. It took me several years to understand. They never explained why they had got this expression, but they have been misleading. So this is natural. The problem is that you notice here it works for two matrices. It doesn't work for three. So two matrices can be simultaneously diagonalized by congruence, two positive matrices. Three cannot. So there is no obvious way of doing this for three matrices till we figured out a connection with the Riemannian geometry. So let n be a smooth manifold. I'm just quickly recapturing some of the ideas. And P hat M tangent space M at the point M. Then I have an inner product so in Riemannian geometry, they call this a metric, which is confusing for an analyst because by metric we understand the distance. But this is called the Riemannian metric. So now given A and B in M, let gamma T smooth curves joining the points A and B. Gamma prime T tangent vector to this at the point P. Then look at the function which I call length of gamma is the integral A to B gamma prime T. Remember now you are moving in the tangent space and in each tangent space there is a different inner product. So this norm will be at gamma T B. That's the length of the curve gamma. So is there a minimizer? Not a thing. So this is the metric in the sense of we understand doing analysis metric spaces. So I've given you a 5-line summary of what we do in Riemannian geometry. You have a manifold, something curved, at each point a tangent space, and each tangent space an inner product varying with the, so the difference from Euclidean geometry, this is varying with m. And then I join any 2 points by a curve, look for the length of that curve according to this definition. If there is a minimizer, that's called a geodesic. And then that's a metric in the sense analysts understand. One good example. So let the manifold M, which I have written there, be positive definite matrices. The tangent space, this is an open set in the set of all Hermitian matrices. So the tangent space at any A is just Hermitian matrix. For X by Hermitian and A positive, the usual inner product would have been trace XY. But what I do now, this is trace A inverse X, A inverse Y. If you believe me and do all that calculation, what you get at the end of it, so I was using D for my earlier metric, I'll use delta for this. So again, some naive comments. Usual metric on positive numbers, we have DAB. Mod A minus B. Logarithmic scale, which we are familiar with, Richter scale or elsewhere, is log A minus log B. Now you have to play with this. If I want, okay, let me write this is also log of A over B. Or B over A, whatever you like. If I want to go to matrices, there are 2 possibilities. I can do log A minus log B. No. That's good, but a bit too simple-minded. If I try to imitate this, I get what I have written. So just as earlier, square root of P minus square root of 2. If I do it in one way, I don't get anything too interesting. If I just change it a little bit, things change. So this is the metric we are talking about. It's the logarithmic scale on matrices. And by the way, the vector version of this is the famous Fisher-Rao metric. They had already done it in classical statistics. Now come troubles if you are not a geometer. Now geometers have metric and then start computing curvature and so on. We feel comfortable if we have equations and inequalities. So I want to know which is the geodesic. Give me A and B and I want a formula for the geodesic. So there are nice inequalities for this metric, semi-parallelogram law and so on. So for an analyst, that's very good. You write parallelogram law first and then you change equation to inequality and some good results pop out.
So if a manifold is the Gaussian measures and you take the trigonometric there, that gives you.
Yeah, I mean, just put,
right?
right. So the inner product there, xy at A, is just something like that. Vectors.
So you get the Wasserstein distance.
No, I'm not in Wasserstein anymore. I'm in this one.
So, but there also you can do optimal transport between like two.
Yeah, but the metric we are talking about is not the same. So, if I have this P with this Riemannian metric, it is standard by the way. It was studied by Cartan and there are theorems which I will quote. But nobody, no geometric book gives us the equation for the geodesic joining A and B. That's what I'm emphasizing. So I want to know, given A and B, in this metric, what's the curve joining A and B, which will minimize the distance. And if you try to write out something spectacular, magical happens. So this is the formula for the geodesic joining A and B. It turns out not a difficult computation, but somebody has to sit down and do it. So that's the equation of the geodesic joining A and B in this metric. So now the geometric mean which I wrote down earlier is just the midpoint of this. So when D is equal to half, you just get this. So this suggests what's a possible good candidate for the geometric mean of more than 2 minutes. So think of the arithmetic mean as the minimizer of the variance. So the geometric mean of A1, A2, An should be the solution of this minimizer problem. So remember, this is my metric now. Now arise the questions, I mean, does this have a solution? Does it have a unique solution? What is it? And so on. Now this again was done way back by Katan. So this has a unique solution and he had studied its various properties. So this is the candidate for a geometric mean of m positive matrices. And the one for 2 variables is a special case of this. Now you have various problems, how to compute this, what is it, does it have the properties I wrote down? So again, geometers didn't worry about order, determinant of this, etc., etc. Now, again, could you tell me the time? Nearly the time. Okay. So maybe 5 to 7 minutes more. So I have to tie it down with the earlier ones. So this has been fairly successful, and in particular, lots of applications in brain-computer interface. So typically what is happening is everybody here knows covariance matrices are positive definite. So you have a radar beam going, hitting something, what you get back is positive matrix valued data. You insert 20 electrodes in my head and look at the currents, you get a 20 by 20 positive definite matrix. And you have to smoothen out the data, which means a good way of averaging. And this turns out to be the best known. So with success of this, one is curious that the Bose-Wasserstein metric I wrote down, is it also a Riemannian metric in this sense? Now here you again have to look into the right books, look at the right theorems, but it is, okay. So it turns out So choose a basis in which A is diagonal. And then for xy Hermitian, the inner product between xy is given by so this looks prettier. It doesn't look that pretty or natural, but it turns out that this is the one which gives rise to the Booth-Wasserstein metric. So now I can ask the same question. What is the Booth-Wasserstein mean of two matrices? What's the Booth-Wasserstein mean of n matrices? I'll just give you the answer, but I don't have time. So Booth-Wasserstein, what to say? This is simply because being analysts, we are not happy till we see equations or anyone. Just saying that this is the curvature, this somehow is not, excuse me for this, it's less familiar for us. So the answer to this is, I'm just using this symbol, it's 1 minus E square A, E square B. That's the equation of the geodesic. And the midpoint of this is the Booth-Wasserstein mean, which is, if you write it, it's 1/4 of A plus B. So some mean of the arithmetic mean, so A plus B over 2, plus the geometric. So it's a mean of between the arithmetic mean and geometric mean of some kind. So that's the midpoint, and it has nice properties. And using this, I can do the same analysis for finding the Wasserstein mean of M positive definite matrix. So I'll end with that. So minimizer of mean square. This is my original metric I was talking about, Booth-Wasserstein, XAD. So this is like Cartman had done it for that metric. So is there a unique answer? And for that, you have to do certain kind of matrix analysis, concavity, convexity, existence of minimizers, etc., etc. So this problem can be solved. And this in turn gives you what is called the multi-marginal optimal transform. So multi-marginal optimal transport, instead of two, so x, y, you have this minimizing x for, so you have minimize this, so you are given m Gaussians, and you want to minimize this, subject to that constraint. The solution to that is, as I explained for 2, solution to this problem, which in turn can be solved using these vectors. So I guess I'll stop here. Then there are various questions about how to compute these things. There are probability ideas which have been used. Just one thing I should say, this turns out to be a manifold of non-positive curvature. So probability theory on manifolds of non-positive curvature has been developed, which can be invoked. So how do I See, for two variables, I gave you an explicit formula. For m, I have just said this, solve that problem. So there is no explicit formula known. So you have to create algorithms to compute it, which people have done, numerical analysis and others. So there's a lot of variety of work on this.
Any question?
Sir, one question. So, we computed the geodesic. Okay? So, is there a way to efficiently find out the geodesic without using the EMI property?
Yeah. So say your question once again.
So, without using the EMI property, is there any other efficient way to?
For this you need EMI and invariant. You see, okay, so what are the problems? Here, this matrix has lots of invariance properties. So this is much simpler. So delta 2 of x star AX, x star BX is delta 2, sorry, I brought in 2 unnecessarily. Let me write it. So delta, this metric, x star AX, x star BX is delta AD. It's invariance under congruences and it's invariant under inversions. So here life becomes easy because I reduce to the case when one of them is using the trick I showed you. One of them is identity, the other is some, so I can use this. This metric doesn't have those invariance properties, so it's more complicated. But then there are theorems like this. You have a Lie group, then you have a group of isometries acting on it, on the quotient. You can pull down geodesics above to geodesics below and so on. So that kind of. So you have to look into the right book for the right theorem to be able to use it. So that's the way it is done.
So,
Yeah.
so as it happened that recently, these means the Lewis persistent mean and the geometric mean, so the remaining structures that have been studied. Recently, I was reading, someone mentioned about Fisher information. So recently, I was reading quantum Fisher information, and they apparently generalize these structures to some extent. And there, I was trying to look at the, the means and geodesics, but there I am not able to have a clear picture because there is no such invariance that I can observe there. So I'm trying to see if I can have some sort of.
Yeah, you have to persist.
But I have not yet been able.
Yeah, I have no answer. By the way, he is working on concavity of fidelity like expressions among other things. So if you want to know more about current relevance in quantum information, he is the person to ask. Yeah.
Any more questions? Comments? Then, anything more to give?
Get them in. Ask anybody online has to.
Oh, can you hear me? I mean, do you have any question online? How, can they hear me?
I think so because they are supposed to hear, but yeah.
দেবাশিস কোনো প্রশ্ন আছে?
না,
Here somewhere, no?
yes, I can hear. না কোনো প্রশ্ন, I don't have any question.
Devashish is here somewhere. Today itself I talked to him. Okay. So Bhatia, just one comment. You in the beginning you mentioned Rao and Bhattacharya. Actually, Bhattacharya was never at ISI.
Never at ISI.
He was at Presidency
All
College. Is it same as Kramer Rao, inequality and Bhattacharya bound? Yes.
What is the full name?
A something. Initials are A.
Only.
So, poet, retirement poet.
ছাত্র হিসাবে
Oh, that I don't know, but he was, I
as a
think,
faculty,
faculty, he was at Presidency College. Anyway, so let's, we have some snacks there. Please take it, otherwise it will go waste. Please become a member of IHIA. Yudho has not yet got. I'm working very hard to do that.
Define that is. That's